So, today we are going to speak about limits and continuity of functions. So, this is our limits and continuity of functions, this is our first story. So, what do I mean by this symbol? You will often find in calculus books. So, limit of f(x) as x tends to a is L, and limit of f(x) as say x tends to infinity is L. And also we are going to explain to you what you mean by limit of f(x) x tends to a is plus infinity or minus infinity, just do it with plus infinity. So, we are going to explain to you very carefully with examples what do we mean by this. Now, first let me understand what I mean by the term x going to a. It essentially means x is coming to a but still not coming, coming but still not coming. As I told you in one of the very first lectures, a teacher explained to me of the notion of a limit in this form. So, this is my a, x coming to a means x can approach from either this side or x can approach from this side. So, x tends to a means the meaning of this is following: given any delta greater than 0, there exists x such that mod of x minus a is strictly less than delta. So, however small delta may be, I will always find an x such that its distance from a is less than delta. So, I can bring, or more to just tell in English language, I can make x come arbitrarily near a. X tends to a means x can be brought arbitrarily near a, but it might not be equal to a any time. Okay, so that is the meaning of x approaching a. So, what is the meaning of f(x)? So, essentially look at a nice function like this, and this is a. So, x approaches a. So, we create a very small neighborhood around a. So, say it is the delta neighborhood. Then we want to see in this particular case, if I take any x here or here, f(x) is in this band. So, f(x) is whatever be the value of, sorry, this is whatever be the, so this is my x axis and this is my y axis, I am not repeating because these are very common things. So, you take a nice function, it is a very nice looking function, smooth and essentially a continuous curve. You see that whatever x I take here, we always have the f(x) lying in this particular band. So, essentially it means that whenever x is near a, when x is near a, in this case the limit here is f of a, but it is not, need not always be. So, when x is near a, f(x) is near L. This is essentially the meaning of this term, limit f(x) x tends to a is L. Now, mathematically how do I put it in a more proper format, and that is again done through the epsilon delta language, which you have to grasp a bit for your understanding. That I say, okay, can you tell me that when x is near a, means if I say, okay, I want f(x) to be within epsilon distance from L. Can you tell me if there is any x which is within some very near A for which this will be true? That is the idea, that if you give me how much I should make fx close to L, I should be able to tell you how much x should be close to A such that for all those x's fx must be close to L within your given prescription. So, given any epsilon greater than 0, there must exist a delta greater than 0 such that fx minus L is strictly less than epsilon for all x such that the distance of x from A is less than L, but x is never equal to A. That is, here we essentially look at a punctured neighborhood, because L may not really be in the domain of f. So, basically you look at the punctured neighborhood. So, here you are looking at what is called the punctured delta neighborhood. So, here this neighborhood is written as A plus delta, A minus delta, and from this set I have taken away A itself. It is called the punctured neighborhood of A. So, because I do not want x to be exactly equal to A, here sorry, it should be delta. So, I am telling that x minus A should be strictly less than delta, that is the distance between x and A. So, the x has to be here or here or here, does not matter, but x cannot be equal to A, because I do not know whether A is in the domain of f. So, that as an example of such a fact, let me consider the function f of x is exponent to the negative power e to the power minus x. If you draw the graph of such a function, you will observe the following. That here the function value is gradually, when I am increasing x, that is in this case where x is going to infinity, when I am increasing x, this value is coming towards for example is bringing me close and close to 0, but there is no x for which e to the power x becomes 0. Another example in this particular case, for example, let me construct here. For example, you take fx is equal to 1 by x. Now, if you look at the graph of this, if you take x is tending to 0, the function value here is going towards plus infinity. As you are bringing x near 0, okay, I am just defining it for x strictly bigger than 0, the function value is coming near infinity. But let me explain to you something very important. When you are talking about a limit, there is also a concept of left limit and right limit. That is, you first have to look at the where the function values are going when x is coming to A from the right side. So, you do not take the A is out. So, when x is coming from the right side, so this is called the right limit, and then you have to also look at the left limit when x is coming from the left side. This A which you have taken out. So, looking at x coming from the left side, what is the relation between these two? If you have equality among them, then you say the limit exists. If you do not have equality among them, then you say the limit does not exist. For example, you will soon learn about a limit, an important limit of this form, limit sin x by x as x tends to 0 is 1. You will soon learn about this limit. This is a very important limit, but you know that this function essentially has no definition at x goes to 0. So, you cannot have, there is no definition of f0 in this case. So, 0 is not in the domain of this function, but still, so that is why you cannot say that this 1 is equal to f of 0 or sin 0 by 0, you cannot say that, because sin 0 by 0 has no meaning. So, this is an example where the function value can approach a limit when it is approaching a given point a, 0 in this case, but that point a might not be in the domain of the function. This is something you have to keep in mind. So, let us again look at limit of fx as x tends to a is plus infinity. What does it mean? And also let us look at limit of fx as x tends to infinity is L. Here it means as x becomes bigger and bigger and bigger, function value approaches L. For example, here if you look at this function fx is equal to 1 by x and you say limit of fx as x tends to infinity, what does this mean? It means that as I am increasing the value of x, where does the function value go? Here it goes down and down and down and down and goes to 0. So, this is some fact you have to keep in mind, you have to remember. Moreover, let us look at something more interesting. For example, if you look at you have an understanding of this, but what is the meaning of this? It says even when x approaches a, for example, in this particular case. So, if you say limit of fx when x is equal to 1 by x and when x approaches 0, then what is the value of fx? The fx value is increasing and increasing and increasing, that is plus infinity. For example, if you take fx is equal to the logarithm of x. So, you know logarithm of x, the domain is only strictly greater than 0. So, again if I approach 0, I am only approaching it from the right hand side, because there is no way approaching it from the left hand side is meaningless, because there is no definition of the function on the left hand side. So, this is log 1 is 0. So, you see what is happening to log x. So, in this case limit of fx as x is coming to 0 from this side, as x is approaching here, this is becoming minus infinity, it goes down and down and down and down. So, the various ways a function can behave depending on the various ways as x goes to a. For example, if you want me to write this, how do I write this in some more some sort of an epsilon delta type thing? Of course, here you do not have epsilon delta business because function fx goes up. What it says that give me any m greater than 0 no matter how large, there exists delta greater than 0 such that mod of fx, right, mod of fx or fx, I am assuming, let us say assume positive function, does not matter, mod of fx is bigger than m if mod x minus a is less than delta. So, whenever x is within the delta neighborhood of a, this is called the delta neighborhood. So, this is always called the delta neighborhood, a plus delta, a minus delta. So, this is an open interval. So, this is an open interval, this is called the delta neighborhood, I am doing a shortcut NBD. So, whenever x is in this, mod of fx would be very large. Of course, you can say that if the whole thing is negative, how can I write? Of course, it will not be negative. If his fx is tending to infinity, at certain time the function value has to become positive. So, you may say that I can just forget the negative values and just concentrate on the positive values and see where it is going when x is approaching the a. If this is the case, then fx must take a positive value after some time, it cannot just stay on taking negative values. If it is having negative minus, it goes to minus infinity, it has to take a negative value after some time. For example, the case of log x, where the function has started taking negative values just after log 1, which is 0, for after x equal to 1, it has started taking negative values. So, till suppose x is approaching 0, so I am coming along this side, the function values are all, the function values are all positive, and then once it crosses 1 and goes more near 0, the function values have become negative. So, these are something you have to keep in mind. We say that f is continuous at x is equal to a if limit of f x as x tends to a is equal to f of a. For example, I can, what is the discontinuous function? Let me define a function. F x is equal to 1 when x is rational is equal to 0 when x is irrational. So, here I am talking about a function to be continuous at a point a. So, if this function is continuous at every x equal to a, we said that the function is continuous throughout its domain. So, here is just an extension of this idea. If f is continuous at each x in the domain, then f is continuous over the domain. Yes, all right. X is rational, x is irrational. Now, what is happening? Let us see. Let us look at this function. So, we are going to test its continuity. F x is 1 when x is rational, 0 when x is irrational. And let me take x naught, a rational number. So, I will check whether at any given rational point it is continuous or not. Okay. So, look at x naught. Now, when I say, so I have to now look at limit of f x as x tends to x naught. What does it mean? How do I look at this thing? Here you see a use of the sequence. To answer such a question, you will need the help of the sequence. This definition of continuity can be written in terms of a sequence. It is as follows. We say f is continuous at a, x equal to a, if for all sequence xn converging to a, f of xn must converge to f of a, then it is continuous. So, if it is not happening, this is not happening, then it is not continuous. So, this idea would be used to understand this problem. For example, so I am asking what is this question. Now, consider a sequence xn of, so you take a sequence xn of rational numbers converging to x naught. So, how will you do it? For example, take any sequence. So, take a sequence like this. So, take a neighborhood around x naught plus delta 1, x naught minus delta 1. So, choose any rational number here, say x1. Then make a much smaller neighborhood which say does not contain x1, right. So, here in this you say that neighborhood can be say x naught minus delta 2 and this is x naught plus delta 2. So, you choose another x2 and you can keep on decreasing the size of the neighborhoods. So, basically now you have considered a sequence and you are decreasing your length of the neighborhood, and each neighborhood you can still find rational numbers coming towards x naught. So, this x1 is a rational number. Now, here you choose some x2 x2, that is also a rational number. So, x1 element of q, sorry I should write it properly, x1 element of q, that is also a rational number. Similarly, instead of rational numbers you could choose irrational numbers. So, let me take a sequence of rational numbers converging to x naught. For if x naught is rational, every fx value is 1. So, if you have a rational sequence xn converging to x naught, where this xn is element of q, then this is 1. But if I take a sequence of irrational numbers xn going to x naught, which you can do, you instead of x1 you can choose a in q, you can choose a something which is in q complement. So, xn is in q complement, so is in irrational numbers. In that case the function value at each of those xn's would be equal to 0. So, limit of fxn would be equal to 0, but the equivalent definition of continuity says that whenever f is continuous at x equal to k, for all the sequence xn that goes to a, fxn will has to go to fa, but here if since x naught is a rational point, f of x naught must be equal to 1, that is the definition of the function value at rational point. So, here if I take a sequence of rational numbers going to x naught, the function the limit value is 1. If I take a sequence of irrational numbers going to x naught, the limit value is 0. So, we have two different limit values, they are not converging to the same value. So, this function is not continuous. So, in the next class we will give much more examples to illustrate all these points in much more detail, and we will calculate, we will take some examples and calculate them. So, thank you very much.